All right. Good morning, everyone. Let's begin with today's class. Um, so before we start doing some work today, I just want to share with you the midterm grades and feedback was I published that. I know some of you had some questions that you were not able to see the feedback. I personally don't know how it looks like on your side, but I know other students were able to see the feedback and the grade. So if you're still having issues, maybe check with one of your colleagues because they may have a better way of helping you to see where you should go to do this, because I don't have the same view as you do on your side. So just an overall thought about the midterm. The average grade was 87.5, just so you have some idea where you are along that average score. There were some questions that were missed more often than others. And so I did send you an email saying this, that if you go back and revisit why you missed the questions you missed, because especially the ones that a lot of people missed may come back on the final. So you don't want to miss it twice. Make sure you check on that. If there's anything in specific that you were confused about, that you maybe didn't understand, maybe the content or the question itself, let me know. Like, I'm always glad to clarify and to correct any mistakes if I made mistakes when I was grading. And we can talk more on that on one-on-one if you wish. I don't want to spend a lot of time going on individual cases in class. So if you have a question or maybe some concerns, let me know by email. I'll be glad to connect with you and go over that. Yes, Ariful, go ahead.
So we'll have final exam,
Yes,
Dr. Vestas. Oh, yeah.
yeah.
Okay.
I'm gonna get to that in a second here. So I have a few items I want to touch base with you all. So the final exam has been scheduled. I was looking to the schedule of the final exam is not something that I set up, is the university that sets up depending on when our class time and dates are. And so I just updated our schedule on the website. So if you go on our page, and you look at the schedule, our final exam is scheduled to be on May 6th from 8 to 11 a.m. So that's going to be our final exam. And again, this date here and time is basically, I guess, dictated by the university. It's not something I chose, but that's what it is for our class dates and times. So it is in our schedule if you want to follow up on that later as well. All right. Also, just a quick, I guess, information from my side. We're gonna have to end a little bit earlier today because I have a commitment I have to run to, but I did not want to have this whole class by, um, by a video. So we're going until 10:50 today. We're gonna leave 20 minutes earlier because of that. Just wanted to let you know. And then lastly, so today we're going to start our machine learning topics. I'm very excited because I think there's going to be a lot of room for us to explore different data sets in some pretty cool ways. And as I mentioned, I guess in the previous class, if you are in like crops and soils and horticulture and things that work with crops outside that make sense for you to work with that type of data set, we're going to have that type of data set for your final project if you choose to do a machine learning final project. As I talked about earlier, I'm going to send you a full instructions on this. But the final project, you're going to be able to choose either if you want to do an experimental design analysis project, which should be from your own data. If you have your own data, you like to do the full analysis on it, get feedback, learn from it, you can do that as your final project. You can also do a machine learning final project. So you do not have to do both. You choose one and you do one of them. If you do decide to do a machine learning final project, we're going to basically you're going to be able to choose if you want to do a outdoors crop type of final project, or if you want to do something else. In class, that something else is going to be one other option. That's going to be food science related. We have a good number of students here that are from food science. And because their research is completely different from what we're doing outdoors with crops, I wanted to give them an opportunity to learn or to explore a data set that's more relatable to them. So if you would like to do a machine learning option with a food science option of that, then you can take that route. Just as a reminder for the machine learning side of things, because we're gonna have basically two groups of machine learning, one working with outdoors type of crops, others working with food science type of data set. And because within each group, you're all going to be working with the same data set, and then it's going to be up to you to maybe, work with create different features out of that data, or maybe train different models, fine-tune different hyperparameters in those models. And in the end, there's also going to be a competition. So I'm going to send you a data set, a holdout data set that you're going to be able to predict using our model. And then whoever gets the best predictive ability of your trained model on that test set, gets first, second, third place. And we may have some awards for that as well. So it's going to be a little bit more, I guess, in a competition way, so if you place first or last is not going to impact your grade, not the fact of you placing first or last. But of course, if you place last because you didn't do the exercise, of course, that impacts your grade. But as long as you do everything that you need to, the ranking does not affect your grade, of course. It's just an extra add-on for us to have some fun there. All right, so before we start our machine learning lecture, any overall comments or thoughts? Yes, Shakir.
Yeah, Dr. Bestos. So regarding the final exam, what's gonna be the syllabus look like? Like what topic should we study for the final exam?
It's going to be comprehensive, so everything is fair game.
Okay, thank you.
Yeah, I mean, I'm going to put more emphasis, of course, on the second half of the semester because that's new content, but you may still get some questions from the first half of the semester. Right, any other questions?
Dr. Bastos.
Yes.
Okay, I can see the k-mean under the multivariate, so we are not doing this k-mean.
You're seeing k-means under multivariate.
And like there are different codes for the PCA and the k-means. Right, we are done with the PCA. So are we doing k-means?
The k-means it's an assignment.
Okay. Sorry.
Yeah, so we talked about that, I think, last class, if you want to revisit that lecture, but that's it. So we're doing k-means as an assignment this time. All right, so if you...
Dr. Bestos.
Yes.
Sorry, I have another question. So where's the weight assigned to the final exam? Like, where's the percentage assigned for the final exam?
So basically, it's going to be 10% as well. So I'm basically, because on the original grading, we had this midterm project, which was going to be the experimental data analysis. So instead of having a midterm and a final project, we're going to have just a final project that can be either machine learning or experimental data analysis. And then this 10% that was for the midterm project is going to turn into 10% of the final exam. Yeah, thanks, Shakir. I guess I forgot to change this to reflect there, but the final is going to be worth 10% of a grade.
Thank you.
Yeah, thank you. And also, I don't know how you see on your side, but I was trying to place the assignments under the assignment category and the quizzes under the quiz category so you can see your grade. And I just made a whole mess on ELC, and I have to fix that. So for right now, don't pay attention to your overall grade on ELC because it's just not correct. But the grade of the midterm is correct. Your percent of the midterm is correct. So just wanted to clarify that. And I'll get that fixed soon here so you can have a better idea of your overall grade. But yeah, just bear with me while I figure out my way around ELC. Okay, so if you go on so today's going to be a lecture. We're not going to be coding today. So if you come here on our schedule, there is a lecture symbol here for machine learning. So today we're going to be talking about a lot of really important concepts around machine learning that will really dictate how we do our code when we get to that part. So if you want to go ahead and launch that presentation, as you know, you can download this as a PDF if you want to take notes on your side. And I'm just gonna get started here, but if you want to follow along with me, you're welcome to. If you want to follow on your computer and, you know, as a PDF to take notes, you're also welcome to do that, or both. All right, so, you know, we're gonna be covering some topics here that I could easily assign you a reading assignment for a lot of the things we're doing. I'm not going to do that. You're all graduate students. If you want to learn more about something, you can do that on your side without me having to ask you and give you a grade for that. So I'm going to give you here a couple of resources that I found very useful, and I used a lot of those resources for this lecture specifically. So one of them is called Tidy Modeling with R. This is a hyperlink, so you can click on that if you're following on the HTML version of this on my website. Tidy Modeling with R is an ebook from, well, I guess RStudio, which now is called Posit. So they basically develop, so as we're aware of, there is this family of packages called Tidyverse, right? So Tidyverse includes things like per, which is the package we use the map function to do iteration. It includes the packages ggplot2, which we use for plots, tidyr, dplyr, and so on. So all these packages from the same developer that follow a similar philosophy and infrastructure. Then RStudio/Posit also developed a package called Tidy Models, which is a similar concept, but it basically is comprised of a lot of smaller packages that are all serving a purpose of doing machine learning in R. And those family of packages and the implementation of those packages are basically used in this book called Tidy Modeling with R. And it's really useful. There's a it's really interactive as well. You see a lot of code, a lot of explanation. So I really urge you to take a look at that if you want to go deeper than what I'm going to be telling you in class. Another one is called Hands-On Machine Learning with R. It's not from RStudio/Posit, yet is a really good resource as well. So both of these are hyperlinks. I use these resources. I used a lot of these resources to make this lecture. So I encourage you to look further into those if you want to do more machine learning in R and learn more than what we're going to be covering here. All right. So my goals for today are going to be to learn the concepts of, first, what is machine learning? We're going to do a quick comparison here between experimental. ST to start AI. Sure. We're going to do a quick comparison of experimental design analysis versus machine learning, because since we're shifting and now fully shifted from experimental design to machine learning, I just want to cover some of the differences there. We're going to then get into a machine learning workflow that's going to look different than the workflow that we've done for experimental design. There's some different things that only apply to machine learning that we need to incorporate into our workflow. So we're going to be talking about that. We're going to be talking about this concept of variance bias trade-off, which is a really key concept in machine learning. And then we're going to cover data spending, or in other words, how do we use the data we have to train a model and be able to create a model that has good predictability on new data, unseen data. We're going to talk about training techniques, hyperparameter optimization, and then predictive assessment. All right, so overall, what is machine learning? So I'm sure there are many different, ways that we can define machine learning, but one of them is just this idea that machine learning is a subfield of artificial intelligence. So machine learning is part of AI. So if you are doing machine learning, you are doing AI. which is broadly defined as the capability of a machine to imitate intelligent human behavior. I think especially these days with large language models, we're seeing the cutting edge ramifications of that. Of course, here we're not going to be creating any LLMs. What we're going to be doing here is basically training models that find patterns in data and are good enough to make predictions on new unseen data, right? So that's the type of machine learning models that we're going to be doing here. And those are applied mostly to tabular data, as we have in our class until now. We're not going to be doing deep learning here. So deep learning would be things like large language models, or perhaps if you're doing very complex artificial neural networks. That is not something we're going to be using here. We're also not going to be analyzing imagery or text or video or even creating those things. Those topics are not covered by this class. We're going to continue using tabular data and going through some of the most popular machine learning algorithms that we use for tabular data. All right, so let's talk about a few differences here between experimental design analysis and machine learning. So in experimental design analysis, the model is most of the time predetermined, right? Like you should know your model even before you collect the data if you were able to design your study, right? You know it's an RCBD with a factorial or 2x3 factorial or whatever factors you have. The model is set. It's pretty much set. We don't play much with it. So we have little room to really play around with that model. We're not going to be adding things and removing things and seeing what makes the model better. The only exception to this is when our assumptions are not met, when the linear model assumptions are not met. So, if you did the repeated measure exercise, that is one situation where you kind of play around a little bit, where you test different error correlation structures to see which one fits the model the best. Or perhaps there are other assumptions that we did not cover in this class that you could also play a little bit around with to make sure you're meeting the assumptions. But that is your goal, is to play around to meet the assumptions, not necessarily to make the model better in another way, except meeting the assumptions. Whereas with machine learning, it's all about playing around with the model. That's what we do. That is what we're going to be doing when we train a machine learning model, is playing around with it. And this playing around comes from the fact that if you think of it, you're going to have a set data, like a set, data frame in front of you that you can apply different algorithms to it. So different machine learning algorithms. Within those algorithms, you're going to have different hyperparameters, which are things that we're going to change to help the model fit the data better. So that's the training part of the model. And even those hyperparameter types, they can have different values. And then you can choose which values you want to train those hyperparameters with that specific algorithm. So in machine learning, it's all about playing around. So an overall workflow of really any data analysis, regardless if it's experimental design analysis or machine learning, is pictured here, right? So you've done this time and time again, each exercise, where we import data, we tidy that data in some way. So this is mostly where we do some wrangling. Perhaps we transform in some way, visualize it, model, and keep the cycle until we come up with our final products that we need, and then we export that to communicate, and that's all happening within a programming environment. In our case, that's R. So this workflow here applies to really any data analysis workflow. So now let's look how this would be adapted to fit a machine learning workflow more specifically. So a machine learning model workflow is going to be split here into 3 major classes or steps. So one of them is going to be pre-processing. This is where we're going to determine how we split our data. This is a very key component. We do not have this in experimental design analysis. It's something that applies to machine learning models. We need to split this data and to spend the data wisely. This is where we do that. Also, any data processing. So we've already done some feature engineering on the feature engineering exercise, but there's other perhaps other feature engineering steps and just data processing steps that we can do, and that would happen at this stage here. After we've done that, we start the training phase. On the training phase is where you specify your model, and we also perform hyperparameter fine-tuning. So this is, so hyperparameters, I guess, we're going to talk more about them in a second, but, well, I'm going to hold it for that, so, because I want to make, I'm going to have some plots to show you to help understand this. After we finalize our training, then we have our validation step. So one key difference here from machine learning to experimental design analysis is with machine learning, our goal is to create a model that can predict. So on experimental design analysis, we're mostly interested in explaining what happened. So we're looking at our study and explaining what happened. We're not trying to use an ANOVA model to predict into the future. That's not our goal. Here with machine learning, it's all about predicting, right? Because of that, we have to validate our models. And so here's where, and this third step is where we would check predictive performance assessment of the final model that you train. So this is the overall workflow. And now we're going to dive into each one of these steps a little bit deeper to understand what's going on. All right, so beginning with the pre-processing step of data splits. Because a major goal of machine learning models is to predict into the future, we have to test, we have to have a data set that our model has not seen when we are checking its predictive power. And even though checking the predictive power model happens at the last step, we need to take that into account in the first step, because this is where we do our data splits. And so for us to make sure that our model is good at predicting unseen data, we need to check for its generalizability. So we want to make sure that it can perform well on data that has not seen, and therefore it's a generalizable model, at least within the context of which it was trained. And the way that we spend our data will help us understand how well the model is going to generalize to new unseen data. So if you imagine here, we have this diagram where we have our whole data set in white. So this would be all rows, all columns of the data set. In our case, I think we have 698, if I remember well, so 698 site years. That's how many rows we would have here on this all data box. And then we need to split it between training data and testing data. So the training set or the training data is what we're going to use to develop new features, train algorithms, fine-tune hyperparameters, compare models, and et cetera. So that's where basically all the training is going to happen on the training data. And then the test data or test set is completely, so once we do this split, we take the training data to train the model, and the test set, we just completely ignore it until the last step. So when we're training the models are not seeing the test set at all. They just have no idea of what data is in the test set. So once we, in the end, when we do determine our best model, train the best model, and so on, we use the test set to make predictions on the test set based on the model that was trained on the training sets. But basically, the test set is, again, this data that you only bring back to your workflow at the last step when you're trying to check how well your model actually performs on unseen new data. So given a fixed amount of data, typical recommendations of what percentage or proportion of your entire data set you should split between training and testing. They vary between 60% on training, 40% on testing. So this would be the percentage of your total rows that would go into each one of those splits. But most commonly, you would see 70-30% splits, or even 80%, 20% splits. There are some trade-offs here, as you would imagine, as you change how much goes into testing, into training, and how much goes into testing. So if you spend too much of your data in training, so let's say you put 90% of your data on training, you won't allow to get a good assessment of the predictive performance because you'll have so few data points on your test, which is what you use to check performance, that perhaps you're not going to have a really good idea of how this model performs on unseen data. And you may find a model that fits the training data very well, but is not generalizable, which in other words, you are overfitting. And we're going to talk a lot about this word and what it means overfitting in a second here. However, if you spend too much of your data on testing, so if you, let's say, keep more than 40% of your data on that testing category, which is only used at the last step, then perhaps your training data is not going to have enough data to really learn from all the examples in your data set. So there's this trade-off. And again, normally a recommendation is if you use a 70% training, 30% testing, is a very common split as you may see on the literature. Yes.
We're assuming all this data is coming from one specific set, like one data set, one experiment, or multiple. Like,
So this would be, I mean, so that question was related to if this data set would be one data set or multiple data sets. Is that?
I guess like one object.
Yeah, I mean, it would basically be whatever is the data that you can bring together that will help you create the model you're trying to create, right? So in our case here, in class, we're going to be using our cotton fiber strength data set. So we're taking all the 698 data rows as our all data, and then splitting that into test and train, right? In your case, let's say maybe you're doing some observational study that it may happen in Georgia, it may happen in the Midwest, it may happen anywhere or at any time, but as long as they have matching both predicted variable and predictor variables that you can combine them, then, it doesn't matter really if it was one study here or maybe one study in the Midwest. As long as you can combine everything, you can still do something like this. Yeah. Charles.
So is there any situation that where you will get like the dynamic data set to a training test? Like when I say dynamic, it's like you continuously getting data. And then you say, okay, you're gonna train and over the lapse of time, I don't know, we're going to say that's something that will happen.
Okay, so let me just rephrase that to those online. So Charles' question here was, what would you do if you have a dynamic data set in the sense that you're getting new data every so often? From experience, I cannot tell you because I don't have that type of data set, but I can tell you the way I would think about it. So if you have dynamic data coming in, I think it would be wise for you to incorporate some of that dynamic data as well and update your model as you go, especially if you have reason to believe that new data coming in may be representing a condition that is not in your original, that is not on the training data that originally trained your model, right? So if you're getting new data and you want to make predictions on that, of course, you would use a trained model and you would have the assumption that the training data is somewhat within the limits of values of the data that you use to train the model in the first place. But if you start getting data that is dynamically coming for you to predict, and some of those data were not represented on your original training data, then I would find a way to incorporate part of that into a new model that you retrained and then make predictions again into that new data as well. So both incorporating to retraining a model and then making also predictions on data that was unseen yet. I think that's probably what I would do. Yes, Comfort.
Yeah, Dr. Bastos, you mentioned at the beginning that the goal of machine learning is for predictive to check like the predictive performance and all of that. But what about models that are used for classifications and clustering? Are they not machine learning also?
So for classification, I mean, both of those could be done in a machine learning framework. But just to give you an idea, so in the data that we're working with, we're doing a regression type of machine learning training because our predicted variable is continuous. If our predicted variable was categorical instead, we would be doing a classification exercise or a classification machine learning workflow. So whether or not it's regression or classification has nothing to do with whether or not you want to predict. It has more to do with what type of predicted variable you have. So we could still, even though again in class we're going to go through a regression example, but if our predicted variable were to be categorical, we would do a classification exercise instead. And there's some differences. We're going to talk about one of them here in this lecture. But the overall workflow remains very similar.
Okay, so you can say everything is more like prediction, but then it depends on what you're predicting, whether it's categorical or continuous variable.
Exactly.
Okay.
Yes, Ashbin.
Dr. Bastos, I'm a little bit confused here. Like for the machine learning, we split our data into training, validation, and test set, right? So,
Well, we're going to get to the points. Yeah.
okay.
It's going slowly here to kind of build the steps to get there. But yes, as you're going to see in a future slide here soon, we're going to further split the training into validation and training.
Okay, thank you. Thank you.
Dr. Bastos,
Yes.
so is it possible to compare machine learning model with the experimental analysis model? For example, I want to see for a particular data set if machine learning model has a better predictability than a regression analysis. So is there any common parameter such as AIC or BIC that I saw in your previous class to compare these two types of analysis?
So if you have experimental analysis data that can be also treated as regression. So regression is really one of the simplest machine learning models that we can have. And then whether or not you're applying in a machine learning context is just dependent on whether or not you're training it or fine-tuning it. So we could do a regression in a machine learning context as well. Normally we would use models that are, I mean, of course, regression can mean a lot of different things, right? So if you think of like a simple regression of a one Y and one X variable, that's very simple. Perhaps you could do a data split if you wanted to have an idea of the generalizability of that model, but there's not a lot you can train about a simple regression model like that. As you're going to see, the models we're going to be using are mostly multivariate models, and they allow for different levels of complexity of the model to model your data. And that complexity degree is what we're going to be training. And so really these models thrive if you have complex data, both related to number of predictors, but also the complexity of the relationships within those predictors and the predicted variable as well. And then I guess your last question about how you would compare. So really machine learning model comparison is going to come down to some very specific metrics where AIC is normally, I mean, you could still use that if you want, but is normally not the one that people report for a machine learning exercise. We're going to talk more about metrics in this lecture, but basically you could compare if you wanted, but it would use different metrics, like the ones we'll talk later in this lecture.
Thank you.
Thanks, everyone. All right, let's keep moving here. So so we need to split the data, right? We need to at least do this initial split here between training and testing. So the two most common ways of doing data split is simple random sampling or stratified sampling. What happens here is we do want our train and test sets to have similar data distribution, especially of our predicted variable, but also of our predictor variables, as we're seeing on the left. So on the left is an example here that I pulled from one of those resources, so it's not ag related, but this is a model that they were trying to predict sale price, I think of houses. And this is just a geom density, and you see two densities there, one in black, one in red. One of those is the density of sale prices, which is the predicted variable, so the Y variable in this model, sale price. One of those density plots is for sales price in training, the other one is for testing. So Charles, going back to your question, you do want your data, your new data coming in to be within the data space of your training set, which this is, right? We're seeing that both of those sale prices for training and testing here are pretty much overlapping. What you would not like to have, regardless if it's dynamic data or not, is if you do your splits in training and testing and you do this plot, and then you have two very separate, distinct distributions. That's something we do not want to have, right? Because if you imagine, if in your training data, you're only training for one specific condition of your predicted variable, and your test data is completely different from that, we would not expect that a model trained on the training data would be able to predict the test because it's just completely different data, right? So this is why we do, so simple random sampling is one way that you can do the split. But if you want to make sure that you have similar representation of your predicted variables in both training and testing, we can do a stratified sampling, which could help us to make sure that training and test have similar data distributions, especially of a predicted variable. And so let's say if you do make this plot here, so we're going to do this plot for fiber strength, and they do not overlap. So there's a term to refer to that when the distribution of a predicted variable between training and testing do not overlap, which is called data shift. And data shift can happen for many different reasons, but it's something that we want to avoid. Because again, if you learn something on a data that looks one way and you use that model to predict something that looks completely different, you would not expect to have a model that is good at predicting that new thing. All right, so after we decide how we want to split our data, what proportion we're doing, and whether or not you're doing random sampling or stratified sampling, then we need to do some pre-processing steps that perhaps are more specific to machine learning models. Different models that we work may require different pre-processing steps. That's going to be model specific. I did leave you here a link if you want to click on this. I'm going to click just to show you, but it's basically so this is a page from that first resource I gave you, Tidy Modeling with R, and it gives here some model types and some of the pre-processing steps that you may need to do, that you have to do, or maybe some that you don't need to do depending on the model. So this is just a resource for you to check as well. So talking about some of those pre-processing steps, it could be imputing NA values. So some of the models we were going to work with, they do not handle NAs, like we saw with PCA, we saw with K-means, which given we did not train them as machine learning models, at least not in the exercises that we went in class. But you notice that they do not handle NA values. So what our solution was well, I guess we did not have NA values in our data, so that was not a problem. But if we had, we would have perhaps dropped those NA values, which sometimes can be a problem because if you drop NA values, you may lose a lot of the data that you have there. So a solution to dropping is imputing those NA values. So this is something that you could do as a pre-processing step before you train a machine learning model. There are different ways we can handle factor levels in machine learning models as well. So this on the pre-processing steps, that's one of the steps that we could take. We could do individual transformations of different variables to handle skewness or lack of normality if the model you're working with is susceptible to that specific feature. We could do discretizing, which basically means if you have a response or if you have a variable that's continuous and you want to create discrete classes out of that, we could do that at this step. Some models are going to require for us to create dummy variables or one-hot encoding. So this basically means, for example, for some models, you can give a categorical column for it and it's going to go with it, no problem. With others, it may not accept categorical variables, so we have to create dummy variables, which is just a numerical way of encoding factors. And this could be done by creating dummy variables or one-hot encoding. You may hear these terms. The main difference here is that dummy variables Let me see if I have an easy way to not overcomplicate this. So basically with dummy variables, let's say if you have 3 different categories, you're going to basically create 2 dummy variables. So you always have n-1 categories is the number of dummy variables you create. And this is very important for especially regression because the matrix requires for you to not have all of the categories as columns. So if you remember when we're calculating degrees of freedom, we always do like A minus 1, B minus 1. That minus 1 is what is making sure that that matrix is invertible behind the scenes. We have not seen matrices ourselves, but behind the scenes, matrices are being inverted, and it requires dummy variables in a way that you have one less column than the number of levels for the matrix to be invertible. With one hot encoding, you basically have 1 column for each one of your categories. So there's no minus 1. That's just a small difference of how the model is trained, but those are 2 different ways that we can transform a categorical variable into a numerical coding. Also creating some interactions, and especially normalization steps. So as you saw, PCA does normalization by itself. K-means does not. We have to do it for K-means. But in many machine learning models will require for us to normalize the variables by centering, scaling, applying the range, and etc. And perhaps some models will require for us, if you have a lot of correlated predictor variables, some models will require for us to run a PCA as a pre-processing step. So PCA not being the analysis we're after is just one of the steps that we're going to do to make sure our features are uncorrelated. So if you remember PCA, one of the things PCA gives us is that the principal components are all orthogonal or independent or non-correlated. So that's why we perhaps need to do a PCA as a pre-processing step of some of these models. All right, so after we define our split, so let's say 70%, 30% in training and testing respectively, and we did all the pre-processing steps required for a given model. Now we get into the training phase. And here's where we talk about hyperparameters. So this is where we first select our model type. So let's just take one example of random forest, which it's a very popular machine learning algorithm. And then we're gonna, once we select that specific model type, then we're gonna start the training process. The goal of the training process is to select the best hyperparameter values that optimize model performance. This, when we say we train a model, this is what we mean, is that we're looking for the best hyperparameter values for that model in your data that optimize predictive performance. So basically, hyperparameters are these parameters in machine learning models that will control how simple or complex the model is allowed to be. And again, you may think, well, just let it be as complex as it can. That's probably better, right? To allow it to be complex. Well, yes, but to a certain extent. An overly complex model actually hurts you. So you don't want, so let's say you have a given data with a given level of complexity that will require to explain the data, and you run a model that's way too simple. That's not good, because the model is not going to be able to predict well future data. However, if you, on the flip side of the coin, train a model that's way too complex, it's also not good. So we need to find a medium between too simple or too complex. And the way we find it is by training your model through hyperparameter fine-tuning. So keeping our example here of random forest, so it has many hyperparameters that we can tune, but 2 of the most common ones that you would see, the first one is called mtry. So this is an integer for the number of predictors that will be randomly sampled at each split when creating the tree model. The default value for this is 1/3 of the number of predictors. So let's say if we have 10 predictors, at each split of each tree in the forest is going to choose a random selection of 1/3 of your predictors instead of choosing all of them. So this number here is something we have to fine-tune, this hyperparameter. Another hyperparameter that we can fine-tune in a random forest model is the number of trees. So the number of trees on that ensemble, on that forest. So we have not talked specifics about random forest yet. So if you have never heard of it, maybe these words are not fully clicking for you. But when we get to that exercise, it will. But basically, it's called random forest because it's an ensemble of many trees. And each tree is going to be, so if you think of mtry, is controlling how many variables each split of a single tree is seeing and which variables those are. And number of trees is just the size of the forest. Normally, the number of trees, you can have a pretty high number of trees and that is not going to hurt you on the too complex side. However, if you have a very complex data, if you have very large data, having an exponentially high number of trees may be computationally intensive. So the reason why we need to look for the best number of trees for your data is because if you can get a good model with 100 trees, why would you do 1,000 or why would you do 1,000,000 trees? So it's more on the side of, you can get pretty high here at the cost of computer power. So if you need a simpler model, let's find the less number of trees that do not hurt your predictive ability of your model. So here, as you would imagine, there's going to be many potential combinations of values between mtry and number of trees that will create the best model for your data. And that's basically what we do in training. We look for those best values for each hyperparameter that you are training. So what happens if we do not optimize hyperparameters? As I said earlier, you may create models that are either too simple or too complex. And because of that, it will not perform well when predicting new data that it has not seen. Then we come to this concept of variance bias trade-off. This is a trade-off. So you cannot optimize both, or you cannot increase or decrease both at the same time. But it's going to be a trade-off that every machine learning model has, regardless of what type of model it is. Every model has this trade-off. So when we look at the prediction error, so let's say you train a model and now you use this model to predict new data that the model has not seen yet. There's going to be an error to that, right? There's going to be a difference between what the model is predicting that it will be and the actual observed value that you can see on your data. So when we look into those prediction errors, that can be decomposed in 3 parts. So that total error is going to be your squared bias, your variance, and your irreducible error. Your irreducible error is something that really there's not much we can do about, but we can play around with bias and variance of your total error and look into how that impacts your prediction. And again, there is going to be a trade-off between your bias and your variance, and we're going to see that in a second here to hopefully help you understand what that is. So let's talk about bias first. So bias is the difference between the expected or average prediction of your model and the correct value that you are trying to predict. And it provides a sense of how a model can conform to the underlying structure of the data. So what we're seeing here is basically some data where you see like it has kind of like this quadratic shape to it. And imagine that this is your full data. And then you do one resampling of 70% testing, 70% training, 30 testing, and then you fit a model to it. And this model here is basically, I don't know, whatever this is. I don't know what this specific model is, but it's a given model, right? That you see is not it's not allowing to really fit the data well enough, but it's fitting okay. Maybe a quadratic model would do better here. But then you do again the resampling of 70-30 and fit again a different model. And then you do again and again and again, and you resample them many times, and each time you fit the same model. You're going to get a slightly different fit each time because the data that goes into training and testing is going to be slightly different each time that you rerun the resampling, right? So basically a model, on the figure on the left, you see the full data set, so not split, and then one of the fits of one time. And then on the right, you're basically seeing 25 times that this data was resampled and the model fits. And each line here represents one time that model was fit to each one of these iterations of splits. And as you can see, the model almost does not change as you resample the data many times. So this model here has high bias. So the model is not being susceptible to slight differences in what data falls into training, what data falls into testing. It is pretty consistent in its response. So this model has high bias. It is very specific and it's not changing too much, which, perhaps is something that would be good. You don't want your model to completely change from one resample to the other. Now, on the flip side of that, there is variance. So variance is the error due to variance is defined as the variability of a model prediction for a given data point. Now, in contrast to the model that we saw on the previous slide, we see here, so let's just focus on the left panel first. So this is a model that has high variance. And it has high variance because it's trying to touch a lot of the points. It's really like trying to be very wiggly here. And it has high variance because on the left, we just have one model fit to one time of this data set. But then if you do the resample again 25 times and fit 25 different models, and each line here on the right represents one of those models, you see that depending on the model, you're going to get a very different prediction of what that model is telling you of the true data. Because now the model is so complex that it's really modeling noise. It's not just modeling the overall structure, it's actually modeling noise. It's trying to touch every single observation. So it is too complex, right? If you bring in new data the model has not seen, I mean, it's kind of hard for us to see, but imagine maybe this line right here on this column. So if you get, this model here, if you get an X value that is somewhere around here, that's just like unseen data that falls around here. If you happen to have the model, this pink model, it would predict this value. And if you happen to have that purple model, it would predict a very high value instead. So what we want to do is we want to be able to create models that are not too strict, like the one on the previous slide, that, I mean, it's kind of taking the shape of the data, but it could have been better, right? It could go up and then down instead of the shape that it has. So this model here has way too high bias. It's not really allowing to even understand the signal of the data enough. However, a model with high variance is then too complex. It's modeling noise. It's capturing the pattern of the data and going a step beyond. It's capturing noise as well. And that's also something we don't want to have. So we want to have models that balance this well, that they are flexible enough to model the signal in the data, but not too flexible to model the noise in the data. That's basically our goal. And so many models are very adaptable and offer extreme flexibility in the patterns that they can fit to, as some of the ones we're gonna train in this class. And because they offer this flexibility, they can run the risk of overfitting. So overfitting is when you fit noise. When you go beyond just fitting the pattern, you're starting to fit noise, and that's undesirable from a machine learning perspective. And it's really interesting, and here is one of the main reasons why we use a data split, because models, so imagine here, let me just come back. If this is your training data, or sorry, let's focus on the left one. If this is your training data, your model is doing a really good job on your training data because it's trying to touch every single point. Great, it basically memorized your training data. But if you bring test data here, it's gonna probably do very poorly, because the chance of your actual test data, which the model has not seen, to fit any one of these wiggles that this line has is very low. So that's why we have the test data, because that's what your model has not seen. It's completely independent. And so that's why we bring here to check how well this model is performing. And so if it is overfitting, so we're going to see some examples of overfitting. So basically you're going to see, well, the model has very high R-squared on their training data, but then when you bring the test, it has pretty low R-squared, meaning that it can predict the data that has seen already pretty well, but new data, it's having a hard time. So this graph basically summarizes this trade-off here. So let's just go through this and walk through this. So what we are trying to do, and I do want to ask for you to look at my screen because I'm going to be moving my cursor around. So what we have here is the predict, or just overall error pretty much on the y-axis, and then model complexity on the x-axis. So as we move right on the x-axis, we're increasing model complexity. What we are trying to optimize here is our generalization error, which comes from your test set, which is this green line here. So what you're seeing, if we just look at the green line, we see that the error of the test is pretty high when your model complexity is low. It decreases until a certain point, and then it starts increasing again when the model becomes too complex, because then you start modeling noise. Why is that? Let's understand what's happening with the other lines here. So the easiest one that we can look is the irreducible error. So this error does not change regardless of the model. Again, that's not what we're really interested here. We're interested in looking at our bias squared and our variance. As you can see, bias and variance are inversely related. As one increases, the other decreases. So there's no way we can optimize both of them in the sense of having both high or both low. We have to find this happy medium where both of them are at their lowest. And we do this by training the model, by doing hyperparameter fine-tuning. That's what basically we're targeting when we're trying to reduce bias at the same time have the lowest possible variance. But something interesting for you to notice as well. Notice this black dotted line here. This is the training error. Your training error will always decrease as you increase model complexity, because your model is learning how to predict your training data to the best possible. It is seeing the data. It knows what's right. It knows how to predict it. So the more complex you make your model, the lower your training error is. So if you're reading a paper and they show you that they're training a machine learning model and they show you R-square or RMSE or any fit metric on the training data only, that's garbage. They can show you the training data fit metrics, okay, but they need to show you the test metrics as well, the unseen data metrics. If they only show you the training data and they say they're doing machine learning, they're really not, because training data R-square will always decrease as model complexity increases. So you need to show the test metrics. That's what really gives you an idea of how predictable or how good of predictive power the model has. So again, if we just perhaps focus in two different lines, notice that the training error always decreases as your model complexity increases. However, your generalization or test error is what we're trying to optimize, which has a happy medium here. It doesn't continually to decrease as model complexity increases. All right, so in other words, a model needs to be complex enough to capture the signal in the data, but not more complex than that, because then it starts capturing noise. So here I bring back to you the same data frame. And in this specific model here, it has one hyperparameter that is called K. So the value of K is what is going to dictate how wiggly this line is, the model line is. I don't know if you can see, but the first one here is saying K equals 2, K equals 5, 10, all the way to 150. So if you imagine now that you are training this machine learning model, you are the algorithm training this, and you are selecting the best model for prediction. What number of K do you think you would choose that would be a good trade-off between too simple and too complex?
10 or 20, I guess.
10 to 20?
Yeah.
Anyone else thinks differently or agrees? 20?
I think 50 to 150.
150?
Maybe
Right.
50.
Yeah. So, I mean, as you can see, a lot of people have different opinions. And of course, when you're training this, it's not going to be subjective. We're going to use metrics that are very objective to help us choose. And I mean, I don't think, maybe if you said 2, you would be wrong. Maybe if you said 150, you may be a little bit wrong because, it's not capturing the true signal at the tails. I would say maybe between 20 and 50. I think I would personally be thinking more of 50, which is this one right here. I think that's probably the one that captures the signal and not trying to be too squiggly and touching every point. But as you can see, it can be subjective if we just visually assess it, right? But thanks, everyone. Thanks for thinking through it. And we're going to use objective assessment to not have this doubt in our heads across us all. All right. So since high variance models are prone to overfitting, we need to do some resampling procedures to reduce this risk. Also, many algorithms that can achieve this high generalization performance, they may have a lot of different hyperparameters that we can control, that we can use to control the level of complexity, which again is going to come down to this trade-off between bias and variance. All right, so, and this, I think Ashmin was mentioning this. Okay, we need to do some validation here as well. So this is where we're gonna now take the next step and further spend our data in a different direction. So we need to optimize hyperparameters of this model so we can balance the variance bias trade-off and create a model that's optimal for prediction. So right now, this is how our data looks like. We had our whole data set split between training and testing. And I told you the testing, we do not touch it until the last step. So we basically put that in a drawer, close it away, don't look at it at all until the last step after we already have a trained model. Which means that for us to find the best hyperparameter values, we're going to have to use our training data for that. And this is where resampling comes into place. So now we're going to basically leverage our training set using resampling models to basically train this model. In this case, we're going to use resampling methods to further split the training set into training and validation, which goes back again to what Ashmin was asking before. So this is just a different way of looking at our data. So we have our whole data on the top. We split first between testing, and testing goes to the right, and training. And again, we do not touch the testing until the last step of this workflow. So we're going to leverage our training. So we're going to use the training and resample the training set in different ways, where each resample, we're going to take that resample and use part of that to test different hyperparameter values, and then the other part of that to do the assessment of that model. And then we're going to do that resample many times. And in the end, when we run all these resamples and now all of our different hyperparameter values, we're going to be able to see which combination of hyperparameter values we're able to optimize the assessment metric. So not on the test yet, remember the test is hidden away, but on the assessment set, which is just a repartitioning of the training. So, yes, Selvin. I can't hear yet.
Oh, yeah. In the previous slide, so the testing, so the analysis and the assessment is like a validation, or is the testing, training, and validation steps?
Yeah. So the assessment is. So I guess you could say, because we take the training and then we split into analysis and assessment, which are just two different ways of perhaps calling training and validation.
Okay. Yeah.
That's basically what it is. All right, so there are different resampling methods that we could use. We're going to talk about some of them here. So one of the most popular is called V-fold cross-validation. We have bootstrapping, we have leave one out cross-validation, and some others as well. So let's explore a couple of these here, just so we see what they mean. Starting with the V-fold cross-validation. Let me make myself. So the V-fold is basically, the V is the number of folds you want to have on this V-fold cross-validation, where the way it works is data are randomly partitioned into V sets of roughly equal size. So in this case here, which are called the folds. So in this case, you can imagine a data frame of 30 rows we see on the left, and then you basically randomly assign each one of those three to one of the V's that you have. In this case here, we have 3 V's, a 3-fold cross-validation. So we have 3 groups. You can kind of see that each one of those observations now has a different color, which is resembling each one of those 3 groups that you just created. Then for each one of those resamplings, 2 of those folds, so we have 3 folds here, 2 of them are going to be used for training the model, and 1 of the folds are going to be used to estimate the model performance. So if you look here on fold 1 iteration, is basically using the folds, well, I guess I'm going to use colors here. So the beige and the blue folds to train the model. And then, so to run a model with a given number of a given value of a hyperparameter, and then it's going to test that model, how well it's predicting on the 3rd fold here, on the green fold. So as you can see on this first fold 1 iteration, the model saw the folds beige and blue, and it was checked how well it was doing on the green one. And then you get a value here of how well this model did. But then it goes on the 2nd fold, where now it takes a different combination of folds being part of the training set, and then another combination of the fold on the test set, or the assessment set, or the validation set in this case. Let me not use test because I don't want to confuse you. So this is not a test set. This is the assessment set, pretty much, that we're looking on the bottom here. And because we have 3 folds, it basically does that for each one of the folds. So on the fold 1 iteration, uses, let's say, folds 1 and 2 to train, and then fold 3 to assess. On the 2nd iteration, it uses folds 1 and 3 to train, and then fold 2 to do the assessment. And then lastly, it uses folds 2 and 3 to train, and then assessment on fold 1. So we have this somewhat independent performance across different folds here, although it's not completely independent, because although within an iteration, you don't have your testing and assessment folds are separate, but you can see how, let's say, that this blue fold here that on the 3rd iteration is on the assessment set, it was on the training set on the 2 previous iterations. So it's not a full independence assessment, but it's a pretty common one. And then in practice, values of V are most often 5 or 10. I mean, 10 is a pretty common number to see in the literature because it's large enough for good results in most situations. All right, so leave one out, cross-validation is also a very common one. But basically, if you have a given number of observations on a training set, you're going to basically fit the same number of models, where for each one of them, you're leaving one observation out. And that's your assessment observation. So let me just perhaps bring this into the context of our class. So we have, right now, our whole data is 698 rows. Imagine that we split that between training and testing. Let's say that we end up with, let's just use an easy number. On your training, we have 500 rows, let's say, of our 698. We have 500 rows in our training. If you do leave one out cross-validation, it means that on the first model, you're basically taking that side ear out, just that one out, and creating a model with all the other 499 observations. And then once you make the model, you use the model to predict this one side ear you left out. That's the first run of your leave one out cross-validation. Now you return that side ear, remove the second side ear, and run a new model that has, again, 499 rows, but which one was in and out is a different one. So if you have 500 rows, you're going to basically run 500 models, each time with one observation being left out, and that is the one that you try to predict. This is what leave one out cross-validation basically is. Okay, that's basically what I said. And so leave one out methods are deficient compared to almost any other method. they perhaps are useful if you have very small data size. So let's say if you have, I don't know, 100 data points, leave one out may be the best, because if you think of it, if you have limited data points, and this is the issue with having fewer data and using that for machine learning, is that if you start breaking your data into different components like training and testing, and then the testing you further split with v-fold cross-validation, you start having very few data points in these different sections of it. And that's the limitation. So if you have small data size, perhaps leave one out cross-validation is going to be the most appropriate, although it's not the one that has the best statistical properties for you to assess model fits or predictability overall. All right, so now we determine the appropriate data splits, the pre-processing, and so now we need to think of what hyperparameters will be optimized and what levels we're going to optimize as well, using which optimization algorithm. So these are all things we have to be aware of when we're making these choices. So if we go back to our previous random forest example, we had two hyperparameters, mtry and trees. Mtry is the number of columns or predictors that each split of each tree can see, and trees is the total number of trees in the forest. So let's say that we try the levels 10, 20, and 30 for mtry, and 10, 100, and 1,000 for the number of trees. How can we test all possible combinations and find the one that produces the most accurate model? Remember, every time you have these hyperparameters, they're not working alone. You have to try different levels of both of them together changing so you can find the best model. So two of the general classes of hyperparameter optimization algorithms are grid search and iterative search. Let's see. We talk about grid search here being our first one. You basically determine you have a predefined set of hyperparameter values that you're going to evaluate. So imagine here that on the x-axis you have mtry, and on the y-axis you have number of trees. Each point here is basically at one. It's basically a grid that's going to test models with this combination of mtry and trees, this combination, and so on. It's going to basically only test models with the specific combination that you define on this grid. It can be inefficient because, again, the number of grid points required to cover the whole parameter space of these two hyperparameters can become unmanageable with the curse of dimensionality. Some of the models we're going to be training may have, I don't know, 8, 10 hyperparameters that you need to fine tune. So imagine that for 10 hyperparameters, you have 3 levels of each one of them, and you're doing all potential combinations of all of those. It becomes a lot of models you have to train, or you have to run to train your model. So one way that we can help with that is to use a iterative search algorithm. In this case here, it's going to sequentially discover new parameter combinations based on previous results. So you still give a starting grid for it, but it's going to start in one of those points, and then it's going to try to navigate this parameter space to see what will be the next combination that it may not be as part of a grid that you created. It's going to be in between the 2 points of a grid, but looking for that space that will optimize your model fit. So in this case here, if I recall correctly, this plot, what it's showing us is these blue lines here are showing you, I think it's one model fit metric, probably R-square. So R-square is being optimized on this top right corner. As you see on this iterative algorithm, I think it probably started down here and then is walking through this parameter space and kind of navigating towards that top right corner on each iteration, because it's looking for the best combination and is not on a fixed grid. It is able to navigate that space outside of a fixed grid. So we need to give some starting values, but then once it starts on those values, it's going to start navigating this on its own and looking for this gradient of where is R-square increasing in this plot, and it's navigating towards that pair of hyperparameter values. All right, so once we do that, so let's say that let me just go back here and tell you a little bit more detail. Let's say we came here and this training process told us that that point right there that I'm highlighting was the combination of hyperparameter values that optimize your assessment set. So let's say that this was mtry, I don't know, 50 and number of trees, 200, whatever it was. Then we take that very specific combination that we found, that we trained, that we found to be the best. And then that's what we say, this is our final model. We just found the best combination. This is our final model. And so we basically select that combination and use that as our final model, and then use that on our assessment, on our training set, then to find our model fit metrics. So I'm telling you, like, best model, best performance, predictive ability, all these terms I'm just using these descriptive words, but now I want to give you some examples of what metrics are used in those steps. In this case here, the metrics you use to judge how well a model is doing is going to depend on what type of predicted variable we have, which comes back to a question that Comfort had earlier. So if we have a numerical predicted variable like we do in this class up until this point, which is cotton fiber strength, then the model is of type regression. And if that's the case, the metrics you use to judge model performance are going to be, there are many of them. I'm going to list some of the most popular here. So one of them is going to be R squared, which is the proportion of the variance in the dependent variable that's predictable from the independent variable, where larger is better. So we want to have high R squared. Another one here is the mean squared error, or MSE, which is the average of the squared error. In this case, MSE, the smaller, the better. Another one that's pretty popular is root mean squared error, or RMSE, which is just the square root of the MSE metric, so that our error is in the same units as your response or predicted variable, and also smaller is better. So if your predicted variable is numerical, you use these types of metrics. However, if your predicted variable is categorical, then your machine learning approach is not regression, it is classification instead. And in that case, we use different metrics. For example, accuracy, which is the proportion of correctly classified data points, both positive and negative. So let's say if we transform our cotton fiber strength that right now is numeric, but imagine you use a histogram of that or a density plot, and we create classes out of that. We call low strength, medium strength, and high strength, depending on the actual number. Now we have a column that is called low, medium, high. So those are classes, those are categories. In this case here, I would be interested in knowing, on average, how well was this model able to predict something was low when it was truly low, something that was medium when it was truly medium, something was high strength when it was truly high. But as you would imagine, there are going to be many other combinations here. Maybe something that was high or that we had a high value of strength is actually classified as low by the model. So that's an error, right? That's a negative outcome of this model. Other metrics here include precision, which is just the proportion of the predicted positive cases that are actually positive. Here is talking about positive and negative more from a binary perspective, if you have two classes only, just for explanation purposes, but it's just for you to have an idea of how they would be calculated. We have sensitivity, which is also called recall or true positive rate, where is the proportion of actual positive cases that the model identifies correctly. And I'm not going to go into the details of the formula itself. Again, we're not going to be doing classification in this class, but if you were to do classification in your work, you do want to go back and read more on these metrics, because each one of them are going to be more useful for different cases. So let's say if for you is really important to predict something. So if you have, for example, a positive or a negative outcome, let's say a disease, for example, it is more important to you to make sure you're predicting when it is happening than to make sure you don't make a mistake of saying that's not happening or that is happening when it's not. It's a little bit confusing, but imagine that you go to the doctor and then you have some type of test. They have some type of algorithm that's going to, based on your blood test, is going to tell you if you have something that you should be worried about. It's better to tell you to worry about when you don't have to than to say you do not have to worry when you have to, right? So to say, well, maybe you have this disease, let's look into it, and you don't have it, great news. Then to say, well, you don't have this disease when you in fact do have it, right? So there's some types of errors that can be weighed differently using different metrics when it comes to classification, that for your research, it may be more important to make one error rather than another. And these are all trade-offs as well. So sensitivity here, true positives divided by the true positives plus false negatives. We have specificity, which is another way of looking into this, whereas the proportion of actual negative cases that the model identifies correctly. And then one that's very common is the area under the receiver operating curve, or AUC-ROC, that measures how well the model distinguishes between those classes. And it's just a different way of looking into this. And again, all these things that I just mentioned, the specificity, recall, precision, and area under the curve, are all things that you only use, are metrics that you use when your predicted variable is categorical. Okay, I have to go in 3 minutes. So let's see if I can get through this. Sorry if I'm rushing, but I think it's going to be important for us to finish today. We can revisit again next class, see if anyone has questions. All right, so now is the third step, the validation step. You develop your model, you train your model, you know exactly what is the combination of hyperparameters that optimize model performance and model predictive ability. Now we're going to check the model predictability on completely unseen data. So now we open that jar, take out that test sets, and this is where we're going to use it. Just out of the way. And so because, again, just a different way of saying this, because the model training process has not seen the test set, these predictions that is going to make on the test set in their performance is what we use to measure how well this model can predict or generalize to unseen data. The whole goal of machine learning is prediction. This is where we do the check. Yeah, Zach. Do you have a question? Oh, sorry, I thought you were saying. All right, so again, coming back to our continuous predicted variable, so doing a regression model, regardless of how complex your model is, you're always going to see, or you should always be looking for this type of plot from a machine learning workflow, where you have observed and predicted. You can show this plot for your training data, but I'm really interested in seeing this plot for your test data, because observed is what we know is the true value of that. So what we measure as carbon fiber strength, and predicted is what the model that we train on another set of data is telling me that cotton fiber quality value is. So this is where we have, so the black line is the one-to-one line. So the closer your predicted and observed pairs are to that black line, the better performance the model has. So we see all the points here where the combination of observed, which is what was truly observed, and the predicted coming from your trained model. And you see that they have a good agreement here. We see R squared of 0.85, RMSE 1.67, and so on. So you normally want to see a plot like this, especially if your predicted variable is continuous. This is one of the plots you would like to see. So models with greater agreements between the predicted and observed, meaning higher R square and lower error metrics, are better at predicting new observations. So we can see that this model, whatever it was, is doing an okay job of predicting whatever was the predicted variable. So in summary, today we basically talked about what is machine learning, some of the differences between that and experimental design analysis. How does a machine learning specific workflow look like? We talked about variance bias trade-off, a very important trade-off here in machine learning, how we spin our data, especially using that test set and further splitting our training set to then train the model. We talked about some training techniques and hyperparameter optimization, and then finally predictive assessment. So I know we went a little bit faster than I wish, especially on this last portion here of these last 10 slides maybe. However, I will have to get going. So what I'm gonna do is I'm gonna just stop recording here.